first the green screen, so I know I'll trim the recording to this. The first thing, since you all had your first assignment due on Friday, I want to be very clear in this class. If you need to sleep, if you need to just time to be a person, we try to be as accommodating as we can. Okay, we can't give you infinite extensions on any assignment. Some days or some assignments, because of where the deadlines fall and the type of feedback we need to give, we might not be able to give a very long extension at all. But please talk to us if you are stressed out or if you feel like I could turn this in on time, but I'm gonna have to stay up all night. If I just had like 6 more hours, I would be so much better. Like, we will accommodate. Please sleep. Please be people. So that's the 6033 news I wanted to cover. I believe on Wednesday I'll finally be ready to talk to you about the Federal Reserve System when we talk about 6033 in the news. All right, so what are we doing today on the networking front? Today we're going to do routing. So I'm going to start the networking lectures by talking about how they fit into this picture. So this is where we ended the last lecture, and in this lecture we were really talking about the internet, right? So the history of the internet, kind of across the top, at least until 1983, which is quite a long time ago now. And we also built up this layered model. All right, so today we're going to start here. We're going to start tackling the network layer. So you've seen a little bit about the link layer in recitation, talking about Ethernet. We're going to start talking about routing today. And I'm going to think about routing in a more general sense. So the styles of routing that you might use on any network, all right, we're not going to talk specifically about the internet today, although this type of routing, both of these types of routing came up in the history of the internet. So distance vector routing and link state routing. But in the back of your mind, just like with pretty much anything in networking, you should be thinking like, well, how would these protocols work on the internet? And for us, a lot of what that means today is how will they scale, right? So today we're going to cover link state routing and distance vector routing. We're going to think about how they scale. And then on Wednesday, we're going to talk about more sort of internet specific routing, right? So before we get into specifics, what's a routing protocol even supposed to do, right? Before we talk about distance vector or link state, right? What's it supposed to do? So the goal of a routing protocol is to help each node of the network figure out a minimum cost route to every destination. All right, so let's see what that means. So I'm gonna start lecture today by drawing you all some pictures. Put that in the center. All right, so let's start with a fairly small network. I'll move this once I have it on the paper. All right, so here, oh, that shows up pretty well, great. So here is a pretty small network. There's only 4 nodes. They're just connected in a square. We're going to spend a lot of time today in every example pretending that we are A. All right, so that's us. All right, now this picture of a network is incomplete, even though it's quite similar to what I drew for you on the last lecture. One of the things that it's missing are costs associated with each link. Okay, so I'm going to make up some costs here. Right, and so what are these costs? Right, like what does this mean? So to some extent, they represent how expensive it is to send a packet along that link. Right, higher cost or expensive, but it's not expensive in terms of like dollars. Right, these costs could represent, in fact, any number of things. We might say if this link, say, is kind of the slowest link in this network, right? So it has the smallest possible throughput here. Well, we'll give that a high cost. We'll say it's going to take a really long time to send data across that link. They might reflect something about latency, right? How long it takes like 1 bit to get from point A to point B. They might reflect something about congestion in the network. So congestion is just a measure of how much traffic is already in the network, right? So if there's a lot of traffic running across a link already, we'll say it's highly congested, right? Perhaps it gets a higher cost. We'll talk a little bit more about those costs in a second, but for now, you can start to look at this goal of a routing protocol and have it make sense for you. All right, so in particular, I'm gonna use a highlighter today. That'll be exciting. All right, if we're starting at A, let's say we wanna get to destination D, right? You can look at this, network and you say, well, okay, there are two paths, right? There's a path that goes A to B to D. There's a path that goes A to C to D. All right, this is easy for us to see because we have the whole view of the network, and this network is quite small and quite easy to understand in many ways. All right, this path has a cost of 7. The cost of the path is just the sum of the cost of the links on the path. This path has a cost of 4. All right, this is the min cost path between those two. So this is the path that we would like packets to take from A to D. And I'll just highlight that so you can kind of remember, right? So, oh, Bitcoin. So these costs, let's understand a little more about them. All right, there's 3 things to know. The third thing is the most important. First thing, these costs are never going to be negative, right? We're not going to have to worry about, like, you know, negative costs don't really make sense here. They could be 0, right? They can also be non-integers. This could be 4.1 instead of 4, right? They can these costs reflect any number of things. They're not going to be negative, right? They also, even though, you know, I draw networks for you like on a plane, they don't have to obey typical laws of geometry. So in particular, you could totally have a network where there's a direct connection between 2 nodes, but it's very expensive. All right, so even though it's the direct path, like A and D are, you know, directly connected, it doesn't mean that's the path that you should use to send packets from A to D, right? They don't have to obey the triangle inequality. Right, so those are nice things to know about costs. But the most important thing for you to know in this class and in life is that these costs can change. They can change over the lifetime of the network. In fact, they can change quite rapidly. This is sort of easiest to think about if you imagine these costs in a network reflecting something like congestion, right? If there's a lot of traffic running across this link, it has a high cost, right? Perhaps if the traffic gets, goes away, it finishes, then maybe we lower the cost, all right? So they can change. That's the big thing that's going to matter for us today. Then, to start to give you some vocabulary, right? When I think about A actually sending packets to D, right? Let's start to do that. And we'll worry about B and C in a second. All right, when A sends packets to D, it's going to send these packets out on the link AC, right? So A to C. And the total cost of that is 4, right? I could start keeping track of these. We can actually figure it out for the other destinations, right? The best path from A to C happens to be that direct link. The nodes don't mean anything yet. They're just 4 nodes in a network. They mean whatever you want them to mean. All right, and then the best path to B looks something like that. All right, so vocabulary time. We will usually differentiate. I try to be really careful about it. Sometimes I slip up between a path and a route. All right, so packets are going from A to D. They're going to take this path that goes A to C and then to D. That's the whole path that these packets would take. But the route from A to D is just this links A to C, right? That is the decision that A has to make here, right? A gets a packet, it's destined for D. A has to send it out on this link. And in some sense, A doesn't really care what happens after that. It just has to get that first hop correct, right? That's going to come up for us today. And then the second piece of vocabulary that I will give you, just so we can talk about this a little bit more precisely and a little bit more in the terms that we actually use in networks. This information, the way I'm sort of writing this down and storing that, that would be a switch's routing table, right? So this is A's routing table. Maybe I even give A route to itself. I want to be very, very precise here. All right, so I'm keeping track for every destination. Here's the route to send packets to that destination. I'm going to keep track of the cost, right? The cost that packets incur going from A to B, A to C, A to D. If you wanted to, if you were building a switch, you could have like a separate cost table. I put them all on one table because it's easier to talk about in a lecture. The actual data structure of a routing table is a little bit more complicated, but routing table is indeed what we call this. And so now that you have sort of thought about this high level goal, right? Remember that in general, we only figured out the correct routes in this network because it was so small. And we could look at it just very quickly and figure out what the routes are. We don't know how we're going to approach this for a big network. But you can now think about what a switch is actually doing in a network. So switches have a couple of jobs. One of their jobs is to build this table and keep it up to date, right? So you're going to build that table, keep it up to date. And that's going to happen periodically, right? In part because costs can change. There can also be some failures in the network, right? In another thing that switches have to do, every time they get a packet, they have to use this table, right? So that is known as forwarding. So when a switch gets a packet, looks at the packet header, parses out the destination. Packet headers are defined in a very, very specific way. It is easy to grab out the destination, look up that destination in the table, send the packet out onto the outgoing link. Is it possible to have different costs going in different directions? It is. I would typically draw that a little bit differently for you. So I might draw you a network with directional links. That has cost 5, that has cost 6, right? So that is possible. We're not gonna worry about that today, but like in theory, yes, right? That is true, right? So this is the type of thing we want a routing protocol to be able to do. And to be able to do these things automatically for big networks, ones where you don't just have like an omnipotent being, which in this case is me, looking at the network and saying, here are the routes, right? So let's make that happen. There are a couple of different ways that we could approach this. Really, there's basically 2 different ways that we could approach this. We could try to design a centralized routing scheme or centralized routing protocol. That would mean that there's some module or some node in the network whose job it is to figure out the routing table for every single other node and just sort of tell them, here are your routes, right? To kind of, just install those routes on those nodes. That is not going to scale at all. We're not even going to consider that in this class. We're only going to think about distributed routing protocols, right? And so what this means is that nodes are going to build up their own routing tables, right? They're going to have to learn about the network on their own. They're going to have to figure out these mid-cost paths on their own, right? With some help from other nodes in the network, but they're making their own decisions. Nobody's coming in and saying, hey, node A, here are your routes. All right, so lucky for us, distributed routing protocols take the same high level approach. We're going to talk about 2 today, but they're both going to follow this same format. All right, so 3 steps. Step 1. So imagine, oh, this will be fun. You're a node in a network, okay, the network of 033 students, and you just turned on, all right? So you know nothing about the rest of the network. You were just born, essentially. First thing you're going to do is learn about your neighbors. Who are the nodes that you're directly connected to? All right, you're going to do this via a protocol called the Hello protocol. The Hello protocol is it's a lot like what it sounds like. All right, a node turns on, sort of has access to its outgoing networking links. It just doesn't know what's on the other end of them, and so it sends a little packet that basically sends hello, right? Hello, like my name is Katrina, right? Every node in the network is doing this. So this node's neighbors are going to respond back with hellos, right? So like if I'm directly connected to Karen and Howie, I turn on, I send them a little thing, says hello. They know who I am. I receive their hellos. Now I know I'm connected to Karen and Howie. And the greatest part of this protocol is that we keep doing it over and over and over until the end of time or until these machines turn off. So as long as Howie and Karen and I are online, right? I keep saying hello, 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 hello. They keep saying the same thing to me, right? So that's how I'm going to learn who I'm directly connected to, right? As a machine, when I turn on, I can tell that I have outgoing links. I just don't know like the name or the address of the node at the other end of them, right? So this hello does that. Almost like, imagine like you walk into a room and you see two people standing there. You're like, well, there are definitely two people here, but I don't know who they are yet. Kind of the same idea, right? Now, one of the reasons we're going to do this over and over and over and over is because the hello protocol is going to help us detect failures. So if I'm directly connected to Howie, but the link between Howie and I gets like severed somehow, right? Someone cuts the cable, or worse yet, like Howie goes to sleep, right? Howie's machine turns off. I'm going to stop getting hello packets from him. I'm going to know very quickly that something is wrong, right? And we'll talk about how to deal with when something goes wrong. So now, okay, hello protocol is going. Everybody knows about their neighbors. What happens next? What happens next is that nodes start to learn about other nodes in the network via advertisements. Advertisements are going to contain some information. The exact information is going to depend on the routing protocol. So I will show you two examples in just a second. But they're going to have some information about other nodes in the network, costs to those nodes. For example, perhaps I start to get advertisements from Howie and Karen, and they tell me about their neighbors, right? Karen might be like connected to Wesley and to Rachel. So I start to learn about the rest of the network. But notice what this implies. This implies that at any point in time in a network, nodes don't necessarily have a global view of the network, right? They don't join the network and automatically know everything, right? They're going to need to infer information about the network from these advertisements, right? And the advertisements themselves can get lost. That's going to cause us some problems today. All right, but once we've sort of started to collect advertisements, nodes will use the information on those advertisements to determine the minimum cost routes. We will often talk about this as integrating advertisements. That's what it means to integrate advertisements here. All right. And so just to recap, these two steps, what's in the advertisements, who gets them, how we use them, that is going to be totally different depending on the protocol. But we're still going to take this high level approach, right? In both cases, there's a hello protocol to learn about neighbors. There are advertisements, and we integrate the advertisements. And then importantly, all of these steps are happening periodically, right? Because link costs can change. It's not enough to figure out a routing table for a network and never change it. The costs can change. So your min cost routes might change. Nodes can join the network or nodes can leave the network, right? Things can fail, right? Links can go down, nodes themselves can crash, advertisements can get lost. Running this protocol periodically helps networks adapt to all of that, right? There might be cases where routes are incorrect for a little bit, right? Maybe we're using a higher cost route than we need to, or something like that. But eventually, things are going to be correct. All right. So to make this more concrete for you, let us actually talk about these two routing protocols, right? If you remember slide 1, history of the internet, distance vector routing historically came before link state routing. I'm going to do link state routing first. I think it's a more natural method of routing. I think it is easier to think about distance vector in the context, in contrast to link state. All right, so how are we going to do this? So first of all, we're going to get really familiar with this example. All right, so this is the example network that I'm going to use for you for both protocols. So this whole time, this is going to be on like the next 1,000 slides. Right? And we're going to start to build up a little bit of a comparison chart, right? So over here on the right, we're just worried about link state right now, but we're eventually going to compare link state and distance vector, right? So that's why I'm leaving some space. So link state, the goal of link state is to disseminate full topology information so that all of the nodes in the graph know the full topology. When I say that they know the full topology, it means that every node in the network has this picture, right? They know all the other nodes in the network. They know the link costs between all the nodes. And then they can take that, treat it as a graph, and run a shortest path algorithm on it. right? So let's figure out how to make that happen, right? The first thing to think about is, okay, what's in an advertisement, right? Here is what is going to be in an advertisement. So we're gonna think a lot about node A, all right? So here's node A. Node A has 3 neighbors, right? E, D, and F. And so node's advertisement is going to contain its link costs to those neighbors, right? So A's advertisement is going to look something like this, right? So it's got a link to B that costs 7. It's got a link to D, cost 2, a link to F of cost 1, all right? So we're using the actual link cost. Because like notice, if you are really on top of this graph already, this link here, that's not the correct route to B, right? Here's a shorter path to B, right? So this algorithm is going to figure that out, but this link cost is going to reflect those neighbors. And then of course, all of the other nodes have their own advertisements, right? B's advertisement says, okay, I have a cost of 7 to link cost of 7 to A, 1 to D, 3 to C, right? So on and so forth. So that's what A's advertisement looks like. Who gets it, right? Where does it get sent? A is effectively going to send this advertisement to everyone, right? And this is going to work via a process called flooding, right? So here's how it's going to work. A has a copy of its advertisement, right? As a little purple circle, that's A's advertisement. It's going to send it out to all of its neighbors, right? So B, D, and F all get copies of this advertisement. As soon as they get it, with some exceptions that I'll come to in a second, as soon as they get it, they're going to forward it to their neighbors, right? So they're going to forward it on. And then, even though, again, we can see here, like, okay, everybody's got the advertisement now, C and E are going to send it to their neighbors, right? This is flooding. So imagine this happening very, very quickly. Someone hands you an advertisement, you say, oh, amazing. You send it out to your neighbors, right? You don't have to wait. You kind of push it right out there, right? Now, I didn't animate it. From what I told you right now, it seems like this process is going to go on and on and on and on. Victoria, in the chat, great question. I'm going to answer that in just a second. All right. So this could go on and on and on. It's not going to go on and on and on. Nodes are going to keep track of which advertisements they forwarded so that they don't forward them again. Right. So imagine when I send an advertisement out, I say, okay, this is advertisement 1. Right. I send it out to my neighbors, Karen and Howie. They get it and they say, okay, I have Katrina's advertisement number 1. Going to just keep track of that, forward it to my neighbors. There's a good chance that another copy of that advertisement might come back around to them. They'll check, they'll say, I already forwarded out advertisement number 1 from Katrina. I'm not going to forward this again. When I go to send my next round of advertisements, so imagine this happening, say, every 10 minutes or so, I send out a new round of advertisements. I'm going to say, okay, this is advertisement 2. Right now, Karen and Howie get it. They say, oh, okay, I forwarded advertisement 1 from Katrina. This is a new one. I'm going to spread that. All right. So that is how, if things change, that's how we make sure new advertisements get pushed up there. And nodes can also be a little bit smarter than what I animated. So I animated this for you, showing that nodes would forward an advertisement even back to the node who sent it. So like A sent its advertisement to B, and then B also forwarded it back to A. They don't need to do that. It just makes it easier to picture. There'd be no reason to do that. All right. So once all of the advertisements are flooded, right? Everybody's gotten it. We're going to not worry about failures right now. Everybody's gotten a copy of A's advertisement. They all know that A has 3 neighbors and the link cost of those neighbors. Similarly, everyone has gotten advertisements from B and C and E and F and D. I don't know if I said all the letters. They've gotten advertisements from everybody. They have this picture, right? In fact, they've gotten a lot of redundant information about this picture. They know all the nodes. They know all the links. They have this graph. That means it's time for shortest path things like Dijkstra's algorithm. If you have seen Dijkstra's algorithm, that's fine. If you've never seen Dijkstra's algorithm, that's also fine. Step 1 is knowing that it's spelled with a J and that you pronounce this word Dijkstra. All right, so let's see what this is like. All right, I will put the algorithm for you in the notes in like a nice algorithmic way. I actually think it's easier though to kind of look at this from the perspective of A and think about what A is going to do. All right, so here's A, and here's A's routing table to start. All right, so what I filled in, it knows about links to its neighbors. So it knows, okay, I got at least a route to B, D, and F, but it doesn't have a route to C and E until it starts integrating these advertisements. And again, we all can look at this this table and say, well, in addition, eventually A needs to discover routes to C and E. This one is going to need to change. That's not the best route to be. All right, so let's see how this works. So Dijkstra's algorithm, it's a good algorithm. In this class, because this is not a theory class, we are not going to spend time proving that it's correct. So you are going to take it on faith and the rapport and belief that we've built up together in these weeks that this algorithm is indeed correct. So here's how it works. We're going to look at this routing table. Is going to say, okay, of all of the costs that I have in this table, which one is the smallest? All right, and that is this cost to F. All right, so in this sense, we know the shortest path to F. That is what we would be proving if this were a class like 6006. All right, so now we're going to sort of look at what F might provide to us. All right, so I'm going to look at each of F's neighbors. All right, the first one is D, and ask questions like, okay, would F give me a better path to D? All right, if A used F to get to D, what would that be like? Well, packets would be taking this path. Right, the cost of that path, 1 + 4, it's 5. That's not better than my current path to D, right? F doesn't provide A with a better route to D, so nothing good really happens there. So let's move on to F's next neighbor, right, which is E. Right, now if A takes packets, it uses F to get to E, that is going to be an improvement. Right now we don't have any route to E, right? This is definitely better, right? That whole path would be a cost of 6, right, which is 1 + 5, right? And again, eagle eyes, this is not the actual best path to E. It's the best path we've got going so far, right? This is going to end up being the shortest path to E. All right, so we've examined all of F's neighbors. We don't need to also look at A. We're already done with A. And so we're done with F. We have visited F now. And then we're going to do this again. We're going to do this and we're going to keep doing this until we have visited every node. What that means for you on the slide, we're going to do this until every node has turned purple. All right, but don't despair, it's going to get faster as we go along. All right, so same process. Look at all of the unfinished nodes in this routing table. Say which one has the lowest cost currently. All right, D. This is our best path to D. We're going to look at all of D's neighbors. All right, all of D's unfinished neighbors. Okay, the first one is B. If I were to take packets on the path A to D to B, that would be an improvement, right? That's a path of cost 3. Our current path costs 7, so we're going to update that, right? So you can see both the route changed and the cost changed. So make that update in the routing table. On to D's next neighbor, which is C. All right, if we take packets from A to G to C, that's a cost of 7, strongly better than an infinite cost. All right, so we'll update that there as well. D has one more unfinished neighbor, which is E. Right, and again, we found a better path to E. All right, so things are getting exciting. Right, we're gonna do the same thing. Right, we've finished D. Right, again, we don't need to visit F. We know the shortest path to F. It's purple on this graph. We don't need to worry about it. So keep going. All right, look at all the unfinished nodes. Which one has the lowest cost? Right, this time it is B. And you can see that what I'm kind of highlighting for you here in this graph is the path that packets are actually going to take to these places. All right, B only has one unfinished node. Right, that is C. Sorry, one unfinished neighbor. Sorry, C. The path A to D to B to C, that is better than what we have. And the way that A could do this calculation is saying, okay, what's my cost to B? which is 3, plus the cost of the link B to C, right? 3 plus 3. All right, so that's 6. So that is going to cause a change in our routing table. Notice that the route itself didn't actually have to change, right? A is still sending packets on the link to D to get them to C, but the cost that those packets are actually going to incur, the path that they're going to take, that needs to be updated. All right, well, that was B's only unfinished neighbor. So we're done with B. You keep going, these last two are going to go very fast because we're going to pick E next. E doesn't have any unfinished neighbors. And then our last node is C, right? This is Dijkstra's algorithm. It is a good algorithm. It has my endorsement, right? So what's good about this protocol? This protocol works. Both of the protocols that we're going to look at are going to work, right? Both of them find shortest paths in a network. The things that differentiate them have to do with what happens when things go wrong, right? Or what happens, how do we think about failures and how do we think about scale? It's going to turn out that how we think about failures influences scale. So what happens when things go wrong? What could go wrong, right? Well, certainly, you know, a link in the network, right, could break. Like this link could go down, right? But in the next round of advertisements, the advertisements will reflect that, right? So yes, this is run periodically. Imagine this running like every 10 minutes. All right, it's run quite often. Right? So if this link goes down, or you know, this node disappears entirely, which means that like all of these links would go down, right? If there's a lot of failure in the network, the next round of advertisements are going to reflect that. Right? It'll be missing those links and that's node, but that's fine. The advertisements will tell me. The more interesting thing to think about is what if advertisements themselves are lost, right? What if we're doing all of the advertising and you know, like Wesley sends an advertisement out on the network and I just don't get a copy of it, right? Or like it doesn't get to Howie and so it doesn't get to me via Howie. Because of the way flooding works, there is so much redundancy in that process. It's actually very rare to find yourself in that case. It is rare that I wouldn't get some copy of, say, Wesley's advertisement, right? Because it means, you know, I'd have to have a failure from all of my neighbors to not get that advertisement somehow. There are so many additional copies sent through the network that actually this protocol is quite resilient to failure. There are pathological cases that you can construct where a failure could get you into a bad situation, but they are quite rare, right? We don't really need to get into the details, right? This protocol really is, it's very robust to advertisements getting lost on the network, right? So this seems like a huge win for link state. But on the downside, all of that redundancy means that there is a ton of overhead in the flooding process, right? Like I send an advertisement out to Karen and Howie, they send it to their neighbors, they send it there's all of this magnification. We're all probably getting multiple copies of advertisements, right? Like I'm gonna get a copy, I'm gonna get 2 copies of every advertisement, right? 1 from each of my neighbors. This is an extraordinary amount of overhead. This is the main thing that prevents a link state style protocol from scaling to the size of the internet, right? There's a lot of other reasons, but we're not going to be able to run a link state protocol across the internet. We would be able to run a link state protocol, say like on MIT's network, right? That size network can deal with this, but this is the trade-off, right? Typically adding a bunch of redundancy makes things more resilient to failure and then increases overhead. So we're going to come back to this. Let's talk about distance vector routing. All right, same example, but it's blue. Okay, so now you know that it's different, right? So distance vector is in some ways going to try to work with less overhead. And it's going to try to, in a certain way, exploit the fact that And this node A, it's really only making 3 decisions, right? Does it send the packets here, here, or here? In a sense, it doesn't really care what happens after that. All right, so distance vector. Advertisements are going to look different, right? They're not going to look different at first, they're going to look different in general, all right? What is in a node's advertisement is its current costs to every node that it's aware of. Eventually, that's going to be every node in the network, hopefully. All right, so if we think about this, this is A's starting routing table. All it knows about are its neighbors. So these link costs reflect the link, these costs reflect the link cost to the neighbors. All right. A's advertisement, A's first advertisement reflects this table. All right. So this first advertisement, it looks very much, in fact, exactly like the advertisement that it sent in link state routing, but that's going to change, right? But this is what's in the advertisement, just basically the routing table, right? Who gets it? Only neighbors. There's no flooding in distance vector, right? So A sends an advertisement to its neighbors. They get it, but they don't forward it anywhere. They just have it now. But all of these nodes are doing the same thing, all right? I've colored them so that we can tell the difference. B is going to send an advertisement to its neighbors. C is going to send to its neighbors, D, E, F, right? Right? So you're going to see something like this, right? All of those advertisements go out to neighbors, right? Which means in the end, they've all received advertisements from their neighbors, right? So you can see like C up here has advertisements from B and D. A has advertisements from B, D, and F. D has advertisements from everyone because it's connected directly to everyone, right? So what are we going to do with that? How does A use this information? Again, there's no flooding, right? I get advertisements from my neighbors. I don't forward them anywhere. So much less overhead on the advertisement side, right? So these are the advertisements that A is going to be receiving from B, D, and F, right? So let's think about how to use those. We're going to go through each of these advertisements, right? I'm going to start with B's and then I'm going to go down, all right? So we're just worried about A for now, looking at B's first advertisement. We're going to go through each individual entry here and just ask ourselves, does this give me a better path, right? Well, B is definitely not going to give A a better path to itself, all right? So that doesn't help us at all, all right? So let's move on to the next one, all right? If A were to use B to get to C, right, that would be a total cost of 10, right? So the cost from A to B, which is 7, plus the cost from B to C, which is 10. Now, I drew a line there. Unless it was, I mean, it can sort of infer at this stage. In general, A doesn't know what path packets are going to take from B to C. It just knows that there is a path of cost 3. And, this is an improvement. This is an improvement for A because it didn't have a path to C. That's great. It's discovered a new node. This is its current cost of that node. All right. Then we'll go through the last one. All right. B has a path of cost 1 to D. If A used B to get to D, that would be a cost of 8. That's not better than what we've got going on here, right? So that's not helping us, right? So that's B's advertisement, done. Now let's go on to D, right? Same process, right? If I used D, and I here am A, right? So if I use D to get to B, oh, that's great. That's going to be a better path, right? 2 plus 1, right? So you can see I've updated the route and the cost here, right? Next one, if I use D to get to C, that's also going to be better, right? Update my route, my cost there. If I use D to get to E, wonderful. We didn't have any path to E yet, right? Add that into my routing table. If I use D to get to F, that's not going to improve anything, right? So there's D's advertisement integrated. Now we'll do the last one pretty quickly because it's not going to help that much. F is not going to give us a better path to A, right? nor does it provide us with a better path to D, nor to E. All right, so A has integrated these advertisements. This is A's routing table after one round of advertisements, right? Note that it hasn't learned the proper min cost route to C yet. It happens to be sending them on the link AD, which is correct, but it doesn't know that this is what's going to happen. So that cost is wrong. Right, so this is what A's next advertisement will look like. Notice that this is different, right? This is different than the first advertisement A sent. That's a difference between link state, right? Link state advertisements from a particular node only change if link costs change. In distance vector, the advertisements effectively reflect the routing table, right? They reflect this information, right? So they change as best paths change, as nodes, as we discover new nodes. And you can, a fun thing for you to do at home, A will update this cost correctly in the next round of advertisements. Right? You should check that out for yourself. It's a good way to test if you understand this algorithm. And again, I will put this algorithm in a more algorithmic form for you in the notes if you'd prefer to see it that way. That's fine. But again, we're not ever going to ask you to prove things about these algorithms. All right. For this class, it's more important to understand kind of at a systems level why they are differing and what is problematic about them. Right. So what's problematic about link state or about distance vector? Failures in distance vector are complicated. They are complicated because of timing. So let me show, we're going to do a fun exercise. And we're going to start with a very simple network. All right, A, B, C, just connected in a line. There's only one route to any other destination. Every link has cost 1. I don't even care about interesting costs for this. And we're going to assume that nodes in this network send advertisements every 10 units of time, right? So 10 minutes, 10 seconds, whatever you want to imagine. But, you know, A and B turned on at different times. So A's sending at time like 0, 10, 20, 30. B is offset. And you can see here, I haven't told you anything interesting about C. That's because I'm going to break the link between B and C. Okay, so this fails. So this update that I've had B make, right? B has now said it learned from the hello protocol very, very quickly that I don't have a route to C anymore. So in this implementation, it's setting the cost of that route to infinity. All right, so INF, imagine that's a constant, okay, infinity. This is a common implementation of distance vector. You could do slight changes, but you'll have the same problems, right? And if we see a cost of infinity to any node, that indicates that we don't have a route to that node, all right? So this is what should happen. This is correct so far. But notice I broke this link at time 9. The next thing that happens is at time 10, right? A is going to send out an advertisement. A's advertisement reflects its routing table. All right, so B says, this is so great. This is so great. I just lost my route to C, but A has a route to C. Amazing. All right, I'm going to update my table. All right, it's the cost from A to C plus my cost to A. So 2 plus 1. Wonderful. And then the next thing that happens, B sends out its advertisement. A will take that advertisement from B, integrate it. And in that integration process, it's going to update the cost. Right? That's something I didn't show you that in the previous example, but if the cost changes, I need to update the costs. And you know, the same thing is going to keep happening. I'm going to bounce back and forth, keep adding these costs until they both get to infinity. So this problem is known as counting to infinity, which, if infinity is a very large constant, as you might expect it to be, this is going to take a very long time. This would be very bad. Like, things fail constantly. We don't want to take this long to recognize a failure, right? So let's try to fix it. There are a couple of techniques that you can use to try to fix this. I'm going to show you one. The reason I'm showing you one is because I want you to see that it doesn't work in all cases, right? So one idea we could have is in a split horizon, right? Split horizon says, you know, if a node is providing you with a route to some destination, don't tell that node about the route to the destination, right? So if A is using B to get to C, A doesn't need to tell B about its route to C. B is A's route to C, right? This case, it's going to be beautiful. Same start, we break the link at time 9, right? And now things look a little different. A's advertisements to B look different, right? It doesn't tell B about any of its other routes because B is providing all of its other routes. So there's no update here, nothing changes, right? And then the next time B sends out an advertisement, right, it'll say, hey, my cost to C changed. A's cost will update accordingly. Wonderful. This is what we wanted to see. We wanted to see these routes to C have cost infinity. Okay, but we can make a slightly different example, slightly more complicated. I'm going to do the same thing. I'm going to break the link between B and C. So all I care about are routes to C. And some of you might have been thinking, sitting here the whole time saying, I am so frustrated. Like, Katrina, the link from B to C broke. Just have B send out an advertisement right away. Okay, like fine. This link fails. C updates its table. I'm going to let B send out the next advertisement. So if all goes well, we'll be set. But all's not going to go well. What if B's advertisement to A gets lost? All right. This means A is going to make no changes to its tables, although D will update correctly. Right. Any argument here that rests on, well, this will work as long as we can get B's advertisement out before A's or D's or something like that, it could get lost. You can't make that guarantee. All right. So, but hey, we made progress. C has correctly inferred. Oh, I don't have a route to C. But if A advertises next, A still thinks it has a route to C. All right. It's not going to send it to B. Split Horizon prevents that. It's going to send it to C though. D is going to advertise, and this is just going to keep going on. Right. We're going to count to infinity. Right. So the reason I want to show you this, it's not because I really care about you understanding all the intricacies of Split Horizon. It's because I want you to see that the timing of advertisements in Distance Vector matters. And that even as you try to improve things, the timing of advertisements, it's uncontrollable. It's uncontrollable because you can't make sure that B sends its advertisement first. There's no way to do that. Advertisements can get lost. This is going to be a problem, right? This limits the size of a network on which we can use distance vector. Because if this problem is going to happen, ironically, we want infinity to be a pretty small number. So in most networks that use a routing protocol like this, infinity is set to like 16 or maybe 32, right? It's infinity in networks is quite small, right? But that means that I can't have a network that has actual large, like high cost paths in it, right? So the failure handling of these two protocols is what limits scale, right? Also, if you're really into distance vector, like if this got you really excited, the next little trick that you can try, which still doesn't work in all cases, has a very good name, which I will just tantalize you with. The next strategy would be Split Horizon with Poison Reverse, which that sounds very cool, but distance vector, it's not going to scale. Okay, so what do we do with this? Neither one of these algorithms, right, will scale to the size of the internet. There's no place where I could use link state or distance vector across the internet, right? It's really no algorithm that's going to work in quite that way. Nor do either of them allow for any sort of policy routing. Remember, we talked about this in the context of the internet, right? Where we get to a point where like NSF says, I don't want commercial traffic on my links. There's no clear way to make this happen here. All right, so this is where we are headed, right? So OSPF, that's a common link state routing protocol. We do see this used in certain places today. RIP is an example of a distance vector routing protocol used on very, very, very small networks, right? But neither of these are going to get us to the size of the internet. So what we're going to talk about on Wednesday is, well, how does that work, right? Clearly, packets from my machine can get to basically any destination. How? Okay, so that's what we're going to do. That's what we're going to do on Wednesday. We're going to talk about my favorite protocol. We're going to have my best music theme at the beginning of lecture. So come back on Wednesday for that. Let me stop recording.